Hello and welcome to another episode of Curiosity Labs Between Two Nerds, where every week we invite a small human being on to have a little chat with us about science. If you have seen us before, welcome back. If you haven't already, please do hit I've got to point in a different direction, that little subscribe button down there, and also hit that bell button, which means we can let you know when we've got new content. If you are listening to us on the podcast and would like to know what we look like, come and have a look on YouTube.com/Between Two Nerds, where you can see our faces.
Yay.
Yeah, why I don't entirely understand why you would want to do that, but you are very welcome. So, straight on, this week we have our oldest guest yet. Still a small human being, but a big small human being.
Not that small.
No, she's making Mo look pretty small.
All right.
So we have a smallish, we'll call it a smallish human being, and this week's human being is...
Tia, and I'm 13 years old.
Awesome. Welcome, Tia. Thank you. By the way, we'll give Tia a little introduction because you won't know this, but if you don't, please check it out. Go and have a look at Team Angel Wolf. You can find Instagram at
Facebook.
Team Angel Wolf.
Yeah.
Facebook, Team Angel Wolf.
Do some awesome stuff.
They do some amazing stuff. So if you want to see a little inspiring story, please do go and check them out. They're amazing. Now, let's see if they know anything about science.
All right. Should we introduce ourselves now?
Oh, yeah, why not? Why not? Who are you?
And you know the nerds. I'm Mo.
And I'm Eugene. Okay.
Okay, Tia. What would you like to ask us or talk about?
How heavy is the Earth?
Okay.
I mean, how much does the Earth weigh?
How much does the Earth weigh?
Yeah.
Should we be pedantic?
Yeah, there's a very pedantic answer to this, which is...
It doesn't weigh anything.
Really?
Yeah, happy with that? The Earth does not have a weight.
So in science, weight means a different thing to mass. So when you talk about mass, you mean how heavy something is, how much stuff it has. And weight is just how much force the Earth is pulling you down with, or any object with gravity is pulling you down with. So the Earth itself doesn't have any weight because its own gravity. But if being less pedantic,
I like that. You could give Earth a weight, but you'd have to move it.
Well, it'll have a weight in reference with the sun.
Yeah, so if you moved it onto the sun, it would definitely have
But even now, it'll have a weight where it is in relation to the sun.
It turns out the Earth does have a weight.
Actually, but because it's orbiting, it'd be weightless.
Yeah, it's falling.
So actually, it doesn't have a weight then.
We'll explain what we're talking about. But if you put Earth on the sun, it would have a weight. You'd be able to work out its weight. If you took Earth and put it on a different star, like a much bigger sun, it would have a different weight.
Yeah.
So the weight is relative to, it was all about what it's relative to.
Which gravitational field you're in. So you have a weight here on Earth, which would be, how heavy are you? How many kg?
I don't know.
Roughly?
Less than 50. Me. Well, let's use me as an example.
Okay, yeah. So Eugene's around 100.
Around
100 kg. So his weight on Earth would be roughly 1,000 newtons. So that's a force. Okay. But on the moon, it would be 1/6 that, which is...
better.
It'd be
18, 17?
2/6. No, that's all right.
It'd be less.
Yeah, it'd be less. 1/6.
Less.
Yeah.
It'd be a lot lighter on the moon. So
Yeah.
my weight would change, but my mass,
Would be...
the amount of stuff that makes me, wouldn't change.
Yeah. So if you're asking so it's just in science we have, in everyday language, we use weight to mean mass, but in science they have different meanings. Okay. So now a less pedantic answer to your question.
That's the answer you actually wanted.
Yeah. So how heavy is the Earth? It's quite heavy.
It's really heavy.
Yeah.
It's heavier than me.
Just about.
All three of us. How heavy do you think? Planet heavy.
Yeah.
It's hard to come up with a point of as heavy as a planet.
So it's something like 6 followed by
24
zeros. Yeah.
Which is a massive number. And 6 followed by 24 0 metric tons. That's right, isn't it?
No, it's kg.
That's kg.
No, that was in kg, yeah.
Ah, that's why it's 24. So 21 zeros for metric tons.
Kg. Yeah, so 6 with 24 zeros after it, which is 6
Septillion.
Yeah,
20.
I think so.
It goes quintillion.
Hexillion?
Yeah, depending.
Well, I don't know. Yeah.
Hex.
Yeah, anyway. So that's how heavy it is.
Huge number.
Yeah.
So a 6 with
24 zeros.
24 zeros for kilograms.
Yeah.
So that's massive.
It's heavy.
That is heavy.
Yep.
But it has to hold us.
Hold us.
Hold us. Not collapse on itself.
How do you know that though?
That's a great question.
That's a good question.
That's science. And maths.
Yeah. Science.
Well, you always need the maths.
Yeah. It's because we have this weighing scale put underneath the earth, stuck underneath,
Scale.
right? And everyone on earth jumped up at the same time and pushed it down onto the scale, right? Well, okay, so how we know that is because of gravity, right? So you know what gravity is, force that pulls us down to the ground, but everything has gravity, right? As long as you have any mass at all. So it doesn't matter, even if it's like a little smote of dust, right? Even that, because it weighs something, right, has gravity. Now, the heavier you are, the more gravity you have. So as long as you can find out how much gravity you have, or an object has, you can work out its mass. So there's a formula. So you know which scientist most famous for, in reference with gravity? If you think of gravity, any scientist comes to mind? Maybe there's a famous story.
Famous scientist.
No.
Big hair.
Oh, right, okay.
Einstein?
Yeah, actually,
Yeah,
one of his
right.
greatest achievements was also to do with gravity, but there's a story about this scientist and an apple.
No.
No? Okay, good, because it's not a true story.
Oh,
It's apocryphal. So there's Isaac
bubble
Newton.
burster.
Have you heard of Isaac Newton?
Sir.
No?
Sir.
So, okay. So Sir Isaac Newton, right, was an English scientist. Right, he was more than just a scientist, really. He's a mathematician, physicist, alchemist, which didn't go so well, right? And so there's a famous story about him sitting underneath an apple tree, and an apple fell from the tree. Either it hit him on the head
Definitely
while he's
hit him on the head.
having a nap, if you're doing it to kids, right? Or
Gave him the, I've had an idea.
right, okay. And so he started thinking about why the apple fell, right? And he discovered gravity. But we say it's apocryphal, it's probably not true, because people knew of gravity before Isaac Newton, like Galileo, and even before that, the ancient Greeks, right? But what Newton did, now Newton is probably the most important scientist of all time.
This is
Right.
about, what, 350
Yeah, 350 years
It's a
ago.
long time ago.
Yeah. He's really famous because he's one of the first scientists that... So what he did was he came up with mathematical formulas to describe just everyday occurrences. So like an object falling from a tree. So he came up with a mathematical formula that could describe that in great detail. Okay, so we call it the law of gravity. And it's written out as... So all laws in science, pretty much, are written out as mathematical formulas, at least in physics. So that means, have you done algebra yet, math, right? So that's one of those where you have letters and you have to put numbers in, right? So there's this famous, the law of gravity was the force of gravity equals the gravitational constant times,
People Google it right now.
the mass of one object times the mass of another object divided by the square of the distance between them. All right.
Just repeat that. Click on in.
Right.
Rewind.
Yes. So just with that formula, right, there's two masses in there. So one would be the mass, let's say, if you wanted to know how much gravitational force there is between an apple falling and the earth, you'd put the mass of the earth as one of the masses there, and the mass of the apple is the second one. As long as you knew the distance between them, you'd be able to calculate the force of gravity. But if you knew the force of gravity to start off with, and you know the mass of the apple and the distance between the apple and actually the center of the earth, right, you'd be able to work out the mass of the earth. So just with gravity, right, so we can,
You got it?
so we can actually see the effect of Earth's gravity on other objects in space, like the moon, and work out the mass of the Earth to a very, very high degree of precision.
Yeah.
Yeah.
It's actually just under 6.
Yeah, 5.97 something. Yeah, yeah. Yeah, so that's how we know. So actually gravity helps us find out things, not just about the Earth, which is very close to us, right? But even things much, much further away, and not just in our solar system, in other solar systems and other galaxies. We can work out how heavy objects are just by seeing their effect, their gravitational effect on other objects around them. That's how we can look at the black hole in the center of our galaxy, which is how far? Something tens of thousands of light years away.
40,000 light years from us.
Okay. So yeah, so we can work out how heavy that black hole is, even though we can't see it, right? Just by measuring its effect on all the other stars around it. So that's how. Yeah.
Then, to be honest, have you followed that?
Yeah.
So we understand the size of stuff gives us, we understand gravity, and then we can work out its mass.
Yeah.
So we can look at models, and computers are very good at this. So we can observe and we can model the galaxy and understand what things should be doing and how things should be moving in relation to each other. But that's actually, when you do that, something weird happens. Do you want to know what? Well,
Yeah, because sometimes those predictions don't always come right. So that means there's something else there that we couldn't, let's say, see or visualize. So that has helped us discover things that we can't even see.
Discover things that we haven't quite discovered.
Yeah. Actually, yeah. That's a better way of putting it.
So we're now looking for stuff that we know exists. So have you ever heard of dark matter?
No.
It's a cool sounding matter. I know it's called. No one really knows why it's called dark matter.
No.
There's debate, isn't
No,
there?
we call it dark matter because we don't
can't
know
see
what it is.
Oh, I've had people argue against me with that there's some other strange.
No.
That's the obvious reason.
Yeah, no, that is the reason. That's why you call it dark matter.
So do you know what matter is? Matter is stuff.
Yeah.
So matter is
So anything
everything.
that occupies space and has mass, right? So anything that is so there's two types of stuff in our universe, right? You can put them into two categories as matter, so anything that occupies space and has a mass, right? And energy, which are things like light. So light doesn't weigh anything, right? So that's energy. So light and heat and things like that. Yeah, so that's what matter is. And there's a dark matter.
You know what dark matter. So because of the conversation and what Mo's explained, which has actually stemmed from understanding the mass of our planet, so we can predict the movement of stuff, of matter. And that matter may be stars, moons, planets, black holes, and the way that the galaxies move. And not just our galaxy, we can look at other galaxies and we can use this to predict. But it doesn't always follow our predictions. So when we look at the way things are moving, if it wasn't, there needs to be more mass there. There needs to be more matter. There needs to be something there to cause these systems to be moving the way they are. So even when you look at our galaxy, if it wasn't for dark matter, our galaxy should have kind of spread apart and bits of it would have flown off and it wouldn't be acting the way it is. So we know that there's this stuff there. Now, and this stuff has mass. And actually it's probably the majority of stuff in space-time, in space that we know about. And we don't know what it is, and we can't see it, but we know it's there.
Yeah, so that's why you call it dark matter. Actually, when you look at this, so you might be able to see, okay, so when you do these predictions, right, you run these models, and then you compare it with what you actually observe. And then it does, if there's some discrepancy between the two, then you know that there's something there that we can't see. Now usually when we trying to look at stuff, even through a telescope, most of the time, we're using visible light, the light that our eyes can detect. But there's a lot, but that's only a tiny, tiny bit of light. You've done the electromagnetic spectrum, I think, in one of Eugene's classes.
You remember it well.
Yeah. So there's radio waves and there's microwaves and infrared and ultraviolet and so on, right? So sometimes we detect huge celestial objects that don't give off any visible light, like might just give off ultraviolet light or X-rays. So we can only see them through like an X-ray telescope or a microwave telescope. That's the thing. I think that's the thing, right? So we can only see them with other types of light. But then the dark matter, though, no matter what wavelength of light we use, we still can't see it. So it's a complete mystery. I mean, there are theories, more like hypotheses, right? Right, that's about what it might be, but we just have no idea. So when we were doing the math, it was just like, so if we look at how, let's say, our galaxy is affecting another galaxy next to us, Andromeda galaxy, I think, so on, we'd see that if we account for all the stuff that we can see and all its gravity, and compare that to the amount of gravitational force felt by the other galaxy from us, something wasn't adding up. I mean, there was a huge difference, actually. And dark matter, I think, is 5 or 6 times more. There's 5 or 6 times more dark matter than there is regular matter.
Yes, 85% of all the...
No, that's when we get to dark energy.
Is that not dark matter? Wait, 5 or 6 times more.
That's a dark, so I think dark matter, regular matter was something like 5%.
The B matter.
Yeah, okay, baryonic something matter. Yeah, right, so that's 5% of the universe. About 25% is dark matter. But there's a whole other 70%, which we have even less clue about. And we call that dark energy. So that's a whole other
thing. This has been a big old answer to how much to do that. You just put a number. Done. Job done. Thanks very much. Oh, right, I've got that. Note that down.
So dark energy is another mystery. So you know the Big Bang, right?
Yeah.
Okay, so from the Big Bang, our universe has been expanding. And we've gone through, at the start, there's a massive rate of expansion. I think that was inflation. Yeah, the first one's inflation, right? And then we went through a slower bit of expansion called Big Bang expansion. And right now, it seems like the rate of expansion is going fast. So we're spreading away from each other faster. But here's the thing now. Yeah.
There's a lot of scientists.
Yeah, so, but here's the thing. So gravity, right? So if you had other forces like, let's say, magnetism or electricity, they have the ability to push things away, right? You know, like if you charge up a balloon and so it tracks your hair, but if you bring it towards another balloon, it can push that balloon away. And same thing with magnets, they can repel each other. But gravity is weird because it doesn't repel. It only pulls things together. So if we have all of this matter with its gravity, and all of this dark matter with all of its gravity as well, then surely one of the theories actually before we could actually detect this expansion was that the universe was going through, was it a big crunch? It was another thing. Yeah. So all this gravity should over time pull everything together, right? But that turns out to be the opposite of what's actually happening.
My theory of multiple universes, which I won't share.
So it seems like the universe, all the galaxies, right, are actually pushing each other away and at a faster and faster rate. So there's some other force, right, that is speeding up the expansion of the universe, right? And we call that dark energy. And if we account for that, that makes up about 70% of the universe.
Now we do know what we don't know.
Yeah.
And that's a big step forward. So we're talking about stuff that we have pretty much no idea about, except for we know it's there. We can evidence that this dark energy, whatever that is there because we can see something is doing something. Dark matter is there because something is doing, and we understand it enough that matter has to be there. But genuinely, barring some hypotheses, we don't know. We just know there's something going on, and there must be something causing what's going on. So now we do know what we don't know, which is a great place for science to be, because when you grow up and become an amazing scientist, I'm not sure that's an ambition of yours,
it should
but
be.
the next generation and the next generation of scientists coming through, what a sort of wonderful puzzle to try and solve. All this stuff, and it's the majority of our universe.
Yeah.
So we think our understanding of our universe is pretty robust, which I guess we're the only measure. So for us, we feel like we're doing well as humans. It's not bad at all. But we now know that the vast majority of the workings of this universe, we have absolutely no idea, and we can't see it. We certainly can't touch it. We don't understand it.
Yeah, so let's say 95% of the universe, you want to say it like that, I guess, right? We don't know a lot about it. But then that 5% we do know, we know quite a bit. we know a lot. Okay, so of that 5%, and that's the bit that so we don't know how dark matter or dark energy especially will affect us regular matter things, right? How much effect it does or doesn't have. But we can explain, because we have such a good picture of all the forces and particles involved that we would ever experience in our everyday life. We have such a good picture of that, such a good theory, like the Standard Model and stuff, right? That for our everyday life, right, we have a very, very good picture of how things work, right, at a physics scale, right? But the stuff that scientists are trying to figure out now, like physics, right, is in more exotic cases, like in black holes and at the start of the universe, at the Big Bang. So that's where we've reached. Now, in our everyday life, we don't have to worry about black holes, right, or the Big Bang, right? But for explaining the stuff that we observe normally, right, we have a very good idea. Yeah.
So how much did the Earth weigh? Do you remember?
A lot.
A lot.
That's a great answer.
Absolutely the right answer. Just under 6 something or others.
6 times 10 to the power 24.
Which is 6.
So when
24
you
Yeah.
yeah.
Just under that, actually. Just under.
Yeah.
That's kg. Kilograms.
Yep, always kg. But math is do you like math?
No, not really.
Are we helping?
Do you like science?
Yeah.
Yeah. Well, math is super important. If you wanted to be a scientist, especially like a physicist or even a chemist, I guess, math is super important, because when we write out these laws, we work it all out in math. We don't just write it in English, right? So if you look, Isaac Newton, his famous book that he wrote these laws, these important laws down, this Principia Mathematica. So it's actually, you could write out all of his laws in mathematical formulas, like on one sheet of paper. And same thing with, that Standard Model that explains just about all the forces. You could write that out as one equation, pretty much.
Yeah.
So math is the language of science, right? We don't use English or, I don't know, Chinese or Arabic, right? No, but math is how we communicate science. So that's what scientists do. Whenever you look at the stereotypical scientist's office, there's all like these
in the movies
gibberish written on, but that makes some kind of sense.
Loads of brackets.
Loads of brackets, loads of symbols, funny ones. You have a regular D and then the partial derivative, which you would have to learn even in like engineering and stuff. We had to do that, and math is super important for it.
So forget science.
Yeah. Or you could just be a biologist, I guess, and ignore the math part.
Marine biologist, that's the dream job. It's my dream job. Clearly, I didn't get it. Following other dreams.
I thought it was a golfer up in
That's
that.
one of them.
Yeah.
Other dreams.
There's been a few.
But that would be the dream proper job.
Yeah.
Marine
What do you want to be when you grow
A
grow up?
professional triathlete.
Oh, that's cool.
That's an awesome thing. That
Yeah.
would make you fitter than me.
I think she already is.
You're en route. You're en route. to me.
En route.
Yeah. Well, yeah.
You've got some catching up to do.
I have. I've no,
So do I. I'm not
I've
even.
no chance of catching up. I'll tell you that one.
All right, I think we should wrap this up.
Enjoy that?
Yes.
Yeah.
Understand any of it?
Yeah.
Perfect. Do you remember the number? How much the Earth weighs?
A lot.
We'll write that. A
Good,
lot.
yeah,
That
yeah.
is exactly the right
Precisely.
answer. Exactly the right answer. Thank you very much for watching. I hope you've learned something and you can remember that number or you've noted it down. Again, if you've enjoyed it and you haven't already, please hit that subscribe button over there. Hit that bell button. If you're way laughing at me,
You look so cool doing it.
hit that. Thanks. I've been practicing. New angles. New angles.
the bell?
I'm very confused. Where's the bell?
Good question.
What's the bell?
The where? Like,
Where is the
I know,
bell? I
there's the
think it's just to the right of the subscribe button. There's a little bell. So see that little
Anyway.
bell, hit that bell, and do hit that like button.
As
If
your
you
next
haven't
guest
already,
is laughing at us.
leave us a comment below
And if you are listening,
if you take issue with anything that we said. And of course, if you're listening, please rate. Is that right?
Yeah.
Rate, hit links, do nice things. It makes a big difference.
spread the word.
Spread the word. Yeah, tell people about it. Your comments so
And
far
check
are
out
lovely.
Team Angel Wolf
Yeah.
on Instagram.
At Team Angel Wolf on Instagram,
They're
Team
awesome.
Angel Wolf on Facebook, who are much more inspiring than us.
Yeah, fair enough.
Less science, Steve.
Yeah.
Less science. We've got science.
All right, Tia, thank you for that. That was awesome.
High
You
five.
were great.
Now you just have to
Great.
wave at that camera relentlessly.
Bye. All right,
It
that's
wasn't
it.
relentless.